You're welcome.
Any more questions? If not, then I was wondering whether we'll have a short break of 5 minutes or so. And then we move to the second session, which will be chaired by Sam.
Yes.
Is that all right?
Yeah, I think a 5-minute break is probably a good idea. What do other people think?
Okay.
I would like to in this talk, I would like to explore the applicability of the Kamloomba model for Bitcoin confirmation times. So earlier in this session, one of the collaborators, Rowel, he has introduced actually this Kamloomba model in the context of Bitcoin as the Bitcoin mempool. And I now want to dive a little bit deeper into the applicability of that model and see whether or not it fits to real data and whether or not we can use it in practice. So my colleague has mainly talked about the Bitcoin mempool and how it can be used, how the Kamloomba model can be used to model the Bitcoin mempool. And then he has discussed some kind of elegant mathematical derivations that show that when there's heavy traffic, so when lots of transactions are coming in, so just about on the border of how many transactions are actually able to be processed by the miners, then there's a nice diffusion approximation. And in this talk, I would instead like to look a little bit more into this model and see how robust is it actually against some of the real world violations that we can expect to see. Because if that's the case, it can be a very useful model in practice. So before I start, I would just like to quickly go back to the Kamloomba model once again and just make sure that we're all on the same page. So the Kamloomba model models the total bytes in the mempool of transactions. So that's that transaction purgatory that Rowel talked about, with all the transactions with a fee byte ratio that exceeds our own transaction. And so this process is easily described. It starts at some initial position, and then over time, there's a steady accumulation of new transactions that come in and are added to the mempool. They each have a higher transaction fee byte ratio than our own transaction. At certain instances, miners find a block, and then the process drops instantaneously by that block size, and then it accumulates again steadily over time. And at some point, there will be no more transactions with a higher fee byte ratio than ours, and that means that the process is at zero. And at that point, we know our transaction has actually been picked up by the miners because it's the one with the highest fee byte ratio. And then we say, okay, at that point in time, our transaction is confirmed. And now we, of course, are interested in the time until the transaction is confirmed. And therefore, we are interested in the time that the Kamloomba model crosses zero. Now, this model makes all kinds of assumptions. The first one is that the blocks arrive according to a homogeneous boson-arrival process. It assumes that the block sizes are constant. And it also assumes that these transactions that come in, they grow steadily, linearly over time. And as all of you probably can guess, none of these assumptions are, of course, completely true in practice. And this is totally expected, of course, but it might still be a big problem. And there's many literatures that discuss various stochastic characteristics of Bitcoin, which also reject the assumptions that we need. So they reject, for instance, the homogeneity of the block arrivals. So does this mean that this model is then, well, a nice little novelty, but it cannot be used? Well, of course, that's still up for debate, because we are really interested in the fact if the violations are severe enough to actually impact our results in a meaningful way. So in other words, I could say, are our results robust to these violations? So on the left-hand side, I have like a schematic overview of the Kamloomba model. So where I've plotted this steady accumulation and these instantaneous drops. Now on the right-hand side, I have some data that has been observed from a certain node that actually looks at, okay, at certain thresholds, how big is the pool of transactions with a certain fee density. And as you can see, they look eerily alike. So there is really hope that these two, this is not some novelty and it doesn't happen in practice. It might actually be a very accurate model. When we zoom in and we look at all those assumptions in detail, this might not actually be the case. So we want to know if our results are really robust. So what do? Well, first we need to know how to measure robustness. So suppose that we have observations, we're just going to call them X, from some adapted Kamloomba model. So for example, I simulate from a Kamloomba model, but instead of having blocks arriving according to a homogeneous Poisson process, they arrive with a non-homogeneous Poisson arrival process. Well, such a model is very hard to analyze, but I can simulate from it. On the other hand, I can denote with F the distribution of confirmation times from a regular Kamloomba model. So one where all those assumptions are met. And this is the model where our theoretical results are based on. Now, I'm of course very interested to see if the mean of my observations X match the mean and standard deviation. So the mean and standard deviations for my observation X, if they match the mean and standard deviation of my distribution F. Because if that's the case, I might conclude, okay, they are very much alike. However, this might not capture everything, and it might be hard to judge, okay, how big is this gap, for example. So a different thing which you can also use is a measure that has a statistically grounded measure that estimates the power of a goodness of fit test. That's going to test whether or not the sample X, so the sample X coming from my adapted Kamloomba model, for which I don't know the distribution, if it fits the distribution F, which is the distribution from the simple Kamloomba model, meeting all assumptions. And if X is very much the same as coming from a regular Kamloomba model, then such a goodness of fit test will have very little power. Whereas if X actually varies wildly in some sense, the power will be high. So we can use the power of this goodness of fit test, and estimate this power, as another measure of robustness. And we could say that things are robust if the power is not much higher than the significance level, for example, because then we are basically under the null. So we're going to use both of these measures and see how they perform. Well, see how certain violations are going to perform, I should say. I'd like to start off with perhaps the most disputed one, which is the homogeneity of the Poisson arrival process. So there are various sources that claim that homogeneity of the Poisson arrival process is not plausible. And actually, if you run yourself some statistical tests, you will also find that, well, if you use sensible tests, that they will also reject homogeneity when you consider large periods of time. And there's a good reason why this is the case. Because when there are more miners searching for blocks, the Bitcoin system is actually implementing something such to basically guarantee homogeneity, but it doesn't work perfectly. So when more miners are searching for blocks, the difficulty of finding a block is adjusted. And in this way, in theory, the expected time to find a new block will always remain constant. Now, if this would have been done in a perfect manner, we would have total homogeneity. But unfortunately, this adjustment is only done periodically. And thus you can temporarily see a different rate of finding blocks. So this has been discussed in various sources, and many of them suppose to instead model the arrival rate with a non-homogeneous Poisson process, with a dependent arrival rate. And this is an exponential function. And then they use a very small value of a, but it will be significant if you look at large timescales. Now the question is, of course, is this a problem for us? Is it problematic for us, basically in a timescale that's interesting to us? Now the answer is no. And this is actually very sensible, because we merely need homogeneity for a relatively short period of time, like a period consisting of one confirmation time. So suppose that you pick A to be 1 over 1,000. Then if I want to compare the means and standard deviations of the confirmation times from my original model and my non-homogeneous model, what I see is that they don't differ by much. And actually that goodness of fit test, when I have 100, a sample size of 100, I estimate the power around the significance level. So it also gives me some confidence that these two models are very much alike. So that's good. So let's move on to another one, a constant block size. So this is not a very unreasonable assumption. Miners have an incentive to fill blocks with as many transactions as they can, because they will reap the transaction fees of each transaction. So it makes sense to fill it up until the maximum. But it is unlikely that they can always fill the block precisely. There might be no transactions available. They might not have sufficient. So it might be that there's a small gap there. Now, if we look into data, we see that blocks are very usually near the maximum. So on the right-hand side, I have a histogram of block sizes ranging from some months ago, and you see, well, they're always almost near the maximum. I should say that these block sizes have been rescaled. I don't want to go too much into these technical details, but a SegWit protocol has been added to the blockchain, which basically rescales how transactions and blocks are weighed, but the end result is the same. So I just scaled things here between 0 and 1. So you see that at many instances, miners just have fill the block near the maximum. But this is not always the case. And we could model this with random block sizes instead. And if I use random blocks, for instance, uniformly between 0.95 and 1, so a very small, not that small uniform period there, and I compare it with an original model where I do adjust the block size to be the expectation of my random block size, I see that there's virtually no difference as well. And also at a 5% significance, the power of the goodness of fit test is again around the significance level. So there's no reason to be worried here. Finally, we have the linear accumulation of the transactions in the mempool. So the picture I showed you before kind of gave the idea that the transactions really flowed in a linear manner. But of course, transactions are added to the mempool at discrete epochs. So very strictly speaking, there can never be linearity present. If I look at larger increments, so for instance, the increment of the mempool size for each minute, they are usually very well aligned, but they're not perfectly aligned, of course. And what I can do is I can model this accumulation with a Brownian motion with a certain drift and volatility. Now we find robustness if the volatility is not too large with respect to the slope. So again, and the slopes and the variances that I see here, they are very much in the safe regime, let's say. And you can also guess, if you look at, for instance, this graphical picture of the mempool size, that nothing really spectacular is going on. So it very much doesn't meet the assumption directly, but it's very benign violation. So, in conclusion, the assumptions of the Kamloomba model are strictly speaking not met, as is the case in all kinds of applications. Now, when we model the various violations that we see in the literature, so a non-homogeneous Poisson process, random block sizes, or a stochastic accumulation process, we see that the effect of these modeled violations on the confirmation time distribution is small. So this is very good, because that means that this Kamloomba model, although simplistic, is very robust against the expected violations that we can see. So it's a very useful model to use in practice, because it will probably give, given this robustness analysis, a very accurate prediction of confirmation time distribution. It can model it pretty well. So that gives us a lot of hope. Now, finally, just to end my presentation, what's next, of course, it will be very interesting to compare observed confirmation times directly with the proposed theoretical distribution. So instead of simulating from proposed violations, I could also just compare observed confirmation times directly with the distribution that I think they follow. However, using such observations in the goodness of fit test is not straightforward, and there are various technical statistical reasons for that. And we are currently in the works of solving these problems. And with that, I want to end my presentation. Thank you very much for listening, and I'm very interested to hear what you have to say.
Great. Thank you very much. Are there any questions?
I have a question.
Yes.
Just about your very last point. Why is the goodness for fit not straightforward? Why is the comparison, or what's tricky in that?
So there's various things going on. Can be basically summarized in 2 points. So first of all, we are fitting a distribution to these observations, but they don't all follow the same distribution. They just follow the same family of distributions. Like they differ in that parameter. The parameter of the distribution that we hypothesize them to be depends on the intensity of the accumulation, which we might assume to be constant over a large period of time. But it also depends on the initial mempool size, and that differs for each observation. So you need to be very careful when you apply such methods. And secondly, and this might be even more problematic, is that in many goodness of fit procedures, we actually assume that the confirmation times are independent, like the observations are independent. Now, because we only have one Bitcoin mempool, we only have one process, we can extract confirmation times there, but I have no guarantee that they are independent unless I first make some modeling assumptions. And then it becomes kind of a chicken and egg problem, because I'm trying to prove that the mempool is a Kamloomba model, in which case extracted confirmation times would be independent, but I will use that basically to verify my first result. So it's a little bit tricky to deal with this.
I see. Thank you.
Great. Are there any other questions?
Yeah, I raised my hand, but I think I already asked my question.
Oh.
So, and I sort of got your answer, Ivo.
Okay.
First of all, I really liked the work, and I also liked the earlier work on this topic that was presented by Rowel. Very nice. Could you remind me then quickly what that distribution is that comes out of the Kramer-Lundberg model? It is the distribution of the number of bits or bytes in the memory pool, right? But is it a steady state or is it a transient distribution?
So the Kamloomba model is just modeling the mempool size, right? Exceeding with transactions exceeding a certain fee density. And then the hypothesized distributions that we have two results. We have a result for any kind of intensity, which is a very complicated expression. And we have a very elegant result in the case that intensity is near the amount of transactions that miners can basically process with their blocks. And that follows an inverse Gaussian distribution.
For these distributions, it's tricky to show that some observed distribution is a fit to that.
So yeah, what we might do for, like, if we are merely interested in looking at transactions with a very high transaction accumulation intensity, so where we can use the fluid approximation, there just using a goodness of fit is not so hard. If we are looking in general, indeed, that expression becomes very hard. So instead of really evaluating the inverse of that expression, which might be very cumbersome, we can simulate from the distribution and build an arbitrary precise ECDF there.
Yeah.
So we can approximate it with simulation again if we would like to. Yeah. So that's not really the main issue here.
Okay. Yeah. Thank you. Thanks very much.
You're welcome.
Great. Well, thank you very much for a great presentation. And
thank you.
Let's move on then. Okay. Next presenting is Vinicius Oliveira, presenting analyzing transaction confirmation in Ethereum using machine learning techniques.
Right. I want to share my screen.
Great.